Thank you very much. It's really a huge pleasure to be a part of this and to see all the wonderful things, especially that Geeta is presenting in her series of lectures, but also to talk about some of the things that we've been doing that I think are a nice compliment from some of the things that Geeta's doing. And I know I've certainly learned a lot from her over the years. And so this is really a pretty exciting series of lectures. So yes, I'll tell you today about some work that I've been doing with my former postdoc, Greg Ongi, who's now a professor at Marquette University, on understanding linear layers in nonlinear neural networks. So as you know, and I'm sure as Geeta's been emphasizing throughout her lectures as well, AI's been experiencing something of a renaissance lately. So we might immediately think of Google's ability to recognize the content of images, or Amazon's recommendations for new products, or Apple's speech recognition in Siri. But really, AI has got an enormous amount of potential beyond these systems. So we're thinking about things like how AI could be used to increase energy efficiency or transportation systems in large cities, accelerate scientific discoveries such as new materials and pharmaceuticals, how to optimally apply fertilizer and pesticides in farm, improve health monitoring and medical diagnostics, forecasting extreme weather events, maintaining industrial equipment, and even order takeout. So as we think about this broad, amazing reach of AI, I think as researchers, there's often kind of two complementary viewpoints that we can take. The first is perhaps a little bit more common. It's that AI is amazing, are capable of doing amazing things, and we should be adopting it everywhere. And within this viewpoint, the focus is really on deployment and efficiency, trying to get something up and running. And the main concern is, can we make something work? Is this at all plausible or possible? So embedded within that mindset is this sort of emphasis on trial and error. And we develop lots of good benchmarks so that we can compare and contrast the accuracy of different methods. And through that process, we innovate quite a bit. An alternative and complementary viewpoint is that AI is very curious. There's lots of things we don't really understand about it. In many ways, it's surprising. And this is an exciting opportunity to learn more. So under this viewpoint, the focus is much more on theory, on the mathematical foundations that Geeta's been telling us about all week, thinking about accuracy bounds, how much data I need, how to design my machine learning system, and more. And so from this perspective, we're really much more concerned with making sure that methods are robust and correct. We're trying to go beyond an initial proof of concept. And in particular, we're often focused on settings where mistakes can be very expensive. So making a mistake when, or Google making a mistake when I ask it to find pictures of cats isn't too much of a problem. But making a mistake when we're trying to make decisions about who should be eligible for a loan or who might have cancer is much more sobering. And so we want to have guarantees on robustness and correctness. And so from this perspective, we have a group of researchers who are really focused on trying to find shortcomings associated with different systems. And not because they're naysayers, but because by identifying these shortcomings, we're going to develop a deeper understanding of these methods, especially a mathematical understanding. And I think progress in the field ultimately depends on both of these viewpoints and approaches. So to give you an example, here's an image or two frames from a BBC Nature video showing a, I would call it a polar bear. The BBC called it an ice bear, I think. And what it's showing is not only these two frames, but it's also showing what a state-of-the-art image recognition system says is the content of this image. So here it's saying that with very high likelihood, it thinks it's an ice bear as opposed to any other kind of animal or object. And the same for this other frame where the bear is standing up instead of on all four paws. But if we were to take this video and then just go forward a couple of frames so that there's a very slight shift in position, all of a sudden, we get very different results from the exact same image recognition system. So now it thinks, well, it might be a baboon or a Madagascar cat or a gorilla, or over here, a weasel is the most likely response. And this is not an adversarial example. I didn't deliberately inject noise or perturb pixels in order to fool this system. These are just slightly different frames from exactly the same natural video that you might watch on TV. And this is the kind of behavior that can be very difficult for us to predict. If we develop an image recognition system and test it out on carefully curated benchmark data sets, then we might see that we're getting generally good holdout performance and miss these more subtle problems that frankly are very problematic and concerning, especially when these exact same image recognition systems are being incorporated into things like self-driving cars. In addition, we could imagine that when we try to train these different machine learning systems, especially deep networks, we can be vulnerable to spurious correlations. So imagine, for instance, that I was going to try to train a machine learning system, such as a neural network, to identify whether an image contains a cat or a dog. And I used training data like this. So this is a little bit contrived because all of the cats are indoors and all of the dogs are in the grass. And so it would be very natural for many machine learning systems to home in on the fact that whenever we see dogs, we also see grass. And of course, this can lead us to making big mistakes down the road. And this is a little silly because of course we can immediately recognize that I've created a training data set that's problematic here, where only dogs are outdoors. But there are many settings where we might have spurious correlations that are much more difficult for humans to interpret or identify and prevent. And so if I was trying to, for instance, design an image recognition system to diagnose disease from chest radiographs, I might have other kinds of correlations that I can't immediately detect. Things on how the image was acquired, or how what kind of image processing we did to smooth it out or remove noise, or even how it was compressed and stored. All of these things can have pretty difficult to predict effects on neural networks used for image recognition and overlook important things like actual pathology or disease. So with this in mind, I think there's a real need to understand how methods like deep neural networks work, what it is they're learning, and where their vulnerabilities are. And we need to go beyond just looking at simple test data sets and instead develop some of these mathematical foundations. So here's sort of a toy diagram of a deep neural network, but these pictures don't truly do it justice. When we look at some examples of very famous neural networks that have been used for things like image recognition or natural language processing, we're seeing, from years ago, 60 million parameters. More modern systems are in the hundreds of billions of parameters. So we're taking limited quantities of data and using that to try to estimate enormous numbers of parameters. And as a result, we're naturally going to be taking that data and fitting it very, very closely. Someone say overfitting it. And I think Peter Bartlett is going to talk about exactly this issue of overfitting in one context later this week. But in addition to these systems having huge numbers of parameters that we have to learn from limited amounts of data, we also have huge varieties of different architectures. So things like feed-forward neural networks or convolutional neural networks that try to extract different kinds of structures from images, or transformers that were developed for natural language processing and also are increasingly being used in imaging applications. So as we think about what is the robustness of these systems, or what kind of accuracy can we expect, or how much data is necessary to learn a good predictor using one of these systems, it's just completely unclear how things like the number of parameters, the size of the network, or the architecture of the network affect what happens. So let's think about this from a slightly narrower perspective. Imagine that we've got a set of training samples that are xi, yi pairs. So the xi's are feature vectors, and the yi's are the labels. And then we're going to use that training data to train a neural network. And we're going to imagine we're in an over-parameterized setting so that we can find weights of the neural network so that we perfectly fit our finite collection of training data, so that we're interpolating our samples. Then the question becomes, well, which interpolating function out of many is going to be selected? So maybe there's lots of different neural network weights that interpolate the samples. Each set of weights corresponds to a different function, and we would like to know, well, which one is actually going to get selected? And how does that depend on the depth of the network or the architecture of the network? And of course, our long-range goal is to understand how these choices affect generalization performance. Okay, so to be a little bit more concrete, let's focus on a over-parameterized feed-forward neural network. So here, just to establish a little bit of notation, our input is going to be a vector x, and in this diagram, it's got 3 elements. That's going to get multiplied by a weight matrix, W1, and then fed into this first set of hidden nodes. So those products of x with different rows of W1 are then going to be fed into a nonlinear or an activation function sigma. And then the outputs of all of those nodes get multiplied by another matrix W2, fed into the next set of hidden nodes, etc. Finally, from the last set of nodes, we get the outputs, and we take the inner product of this set of outputs with a vector A, and that gives us our final output. So I'm going to call this H theta L of x to emphasize the fact, first of all, that whatever is coming out of this network is just a function of the input. So this network here is just one way of representing a function. Theta corresponds to the set of all the different weights or parameters in the network that I have to learn. And L is indicating how many different layers there are in this network, so the depth of the network. And so here I've explicitly written out what this network is doing in this functional form. So once I've set up a network like this, then once I get my data, the way that I choose these weights, or the way that I learn the values of W1, W2, all the way through to A, is that I say, all right, I'm going to search among all possible sets of weights and choose something that gives me a small loss so I can measure how well this function H theta fits my observations, plus often some sort of regularization term, which I'm going to call C sub L, where C is a cost, and L is the number of layers in the network. And the most common form of regularization that we see is weight decay, where we're basically penalizing the sum of the squares of all of the weights in the network. So there's a couple of reasons that we're interested in weight decay. One is that empirically it works well, so this is actually used in practice quite a bit. Second, it's got close ties to ideas from ridge regression and linear algebra. And again, I believe that we'll see some more about this from Peter's talk later this week. And thirdly, even if we don't explicitly use weight decay regularization, and we just try to measure minimize some measure of data fit, if we use tools like stochastic gradient descent in order to solve this optimization problem, they often implicitly induce some sort of regularization, even if we don't explicitly put it into our code. And so for many reasons, this is a very important form of regularization to understand. Okay, so I want to think about now what's happening when we train a neural network this way and use that training to learn a function. So I want to transition to a function space perspective. So everything on the top here is just what we had on the previous slide as a reminder. But equivalently, we could think about what's happening like I've got here on the bottom. So what we're doing when we search over different neural network parameters is that we are searching over functions, each function being represented by the network. And we're trying to choose a function that has a small value of the loss, or basically we're seeing how well it fits our data, and some regularization, some function R that I'm going to call the representation cost, that tells us which functions F are more preferred or less preferred when we're trying to fit data by searching for a function represented by a neural network. So just from where we are so far, we can define very easily this representation cost as corresponding to the minimum over all possible neural network weights of this weight decay term, of this sum of squares of all the weights, where we constrain our search to all the different networks that fit our function F. And so the question here then is, how can we characterize this representation cost, right? I can write this in terms of the network weights, but I want to understand more, what's the nature of a function that has a small value for this representation cost versus a large value of this representation cost? Another way of looking at it is like this. So again, imagine that we've got a finite collection of training samples, features, and labels. And the way that we normally might set this up when we train a neural network is we might say, let's search over all neural network parameters so that we fit our data perfectly using that learned neural network. And among all the different weights or parameters of the network that fit our data, we're going to choose a set of weights that has the smallest value of this sum of squares. So equivalently, when we're doing this interpolation process, what we're really doing is we're searching over all different functions that can fit our data, that interpolate our data, and we're choosing the interpolant that has the minimum value of this representation cost. So if I'm going to try to interpolate samples using a neural network, what I'd like to know is, what kinds of interpolating functions am I going to choose? Am I going to choose something that's really wiggly and oscillatory? Am I going to choose something that's very smooth? What are the kind of preferred functions that I end up learning? And what we find empirically is that if I were to change the architecture of my network, then I end up getting different interpolating functions. And so we'd like to better understand, well, what is the role of the architecture of the network? And that plays into some of these earlier questions I raised, such as trying to understand the robustness of methods or having guarantees on the correctness. We'd like to have some sort of mathematical guidance as we try to find good network architectures to solve real-world problems. So there have been some past efforts that are aimed at trying to understand representation costs of neural networks and trying to understand this function space perspective. One line of work has focused on two-layer ReLU networks. So in this setting, there is only one hidden layer of nodes, and this activation function is, if we call this sigma of z, then it's z if z is positive and 0 otherwise. So a very common form of activation function used in practice. And so a few years ago, Saravisi and his team showed that if all of our features are scalars, then this representation cost for a two-layer ReLU network corresponded to the integral or the L1 norm of the second derivative of the function. And so if we were to try to interpolate samples using a two-layer neural network, ReLU network like this, we'd seek functions that have a small value of this L1 norm of the second derivative. So we'd seek that kind of smoothness in our representation or in our interpolating function. Soon after that, my co-author Greg Anji and along with Daniel Sudri and Nadi Cerebro extended this to settings where the domain X could be much higher dimensional. And we found that, this representation cost really reflects what happens if you were to take the total variation norm of this function after computing its Laplacian and then the radon transform. And so we got a lot of insights into what was happening when we tried to train very wide two-layer networks, and more recent work has built upon that work to try to develop Banach space representations and representer theorems along with minimax rates. But all of this is explicitly limited to a single hidden layer. So some additional and parallel work has focused on many more layers, but linear networks. So here, all of the activation functions and all of the hidden nodes are just linear. So there's no nonlinearity at all. We're just fitting linear models to data, but doing it using a neural network. So in this setting, G and Telgarsky showed something about how performing gradient descent on these linear networks gives us some notion of layer alignment. And this is a concept I'm going to dive into in a couple of slides, so I'll just leave it at that for now. More recent work by Dai, Karzan, and Cerebro showed how altering the architecture in these linear networks can induce different kinds of regularization. But the focus of this talk today really is on networks that have multiple layers and have nonlinear activation functions. So a significant step forward from both two-layer networks or only linear networks. Some related work has explored this in the context of settings where all of the data is along a line or orthonormal. The work I'll talk about today, I think, complements that and considers more general data settings. So let me be explicit about what we want to do here. So to start, let's imagine a basic two-layer ReLU network. So what this diagram is representing is the following. So we take an input X, and we're going to take its inner product with a vector WK. So that would correspond to, if I'm thinking about this first node, all of the weights of these lines feeding into that first node. So I compute that inner product and add a bias that's not shown in my diagram, and then feed that into a ReLU unit. So I leave it alone if it's positive and set it to 0 if it's negative. I then take the output of that ReLU network and multiply it times another weight A sub k. I do this for each of the hidden nodes, add a final constant, and then that's my final output. And I can write this in shorthand this way, where W, this big W here, are all the weights for all the inputting to all the hidden nodes in the network. So in this setting, theta, the set of all the weights that I have to learn, is this matrix W, this vector A, the biases B, and the constant offset C. The way that we are going to build upon that basic two-layer ReLU network is by considering networks that have L layers, where L minus one of them have linear activations, and the final layer has got a ReLU nonlinearity. So in particular, we're going to take our function X, our input X, multiply it by W1, then W2, all the way to WL minus one, add a bias, feed it into our ReLU network, our ReLU units, take the inner product of those outputs with this vector A and add a constant. So one of the things that I want to emphasize is that if I were to multiply all of these W's together and then just call them a single W, I actually have a function that's the exact same functional form here as I had with a two-layer neural network. The key difference is that now theta, the set of all the different weights or parameters that I have to learn, WL minus one all the way to W1, A, B, and C, is different than the set of weights that I have to learn with the two-layer network. Okay, so let me kind of make that hopefully a little bit clearer. So if I were to compare a two-layer network and a three-layer network, then in both cases, I can represent them with this same basic functional form, where W here is the product of the two different weight matrices around the linear layer, W2 and W1. So I'm representing similar types of functions, but the key distinction is that when I do this weight decay regularization, when I try to regularize which weights I learn in my neural network, that's different. So with a two-layer network, I have the 2 norm of A squared plus the Frobenius norm of W squared. Whereas when I've got a 3-layer network, then I've got the 2 norm of A squared, the Frobenius norm of W1 plus the Frobenius norm of W2. So the main difference here is the way in which we perform the regularization. So you might ask, well, why is inserting these linear layers something that we should be interested in? Why is this the next extension that's exciting and important? Well, one reason for that is that as I add these different linear layers, I'm not changing the expressivity or the capacity of the network. So no matter how many layers I have, I'm generally learning functions of this basic form. The only difference is in how it's being regularized, because I'm representing it differently with different sets of parameters. And so by exploring this family of networks, when we see different behaviors for different depths, we know that that's not because all of a sudden we're, say, working in a richer function space. We're working in the same function space. We're only seeing the role of depth in terms of how it affects which function within this function space we're choosing to interpolate our data. Okay, so that's one reason. It really just helps us narrow our focus into the role of depth without complicating it with thinking about different function spaces. In addition, there's been empirical evidence that when we add linear layers, we can generally get better generalization performance. And so this is just a good thing to do in practice. There's also been some work done more from the optimization perspective, showing that linear layers can help training speed, or even trying to understand the dynamics of optimization in linear networks using stochastic gradient descent. Even some of the more theoretical work that's tried to do function space representations of different neural networks of different depths has incorporated this notion of a linear layer. And I think in part that's because it facilitated a clean and nice theoretical framework. Okay, so our goal then is within this setting to characterize these representation costs RL. So remember, we said that if, for instance, if we were going to interpolate a finite number of samples, we're going to choose the function that fits the data that has the smallest representation cost. So we really want to understand, well, what this representation cost is so that we can understand what function we're going to choose to interpolate our samples. So in past work, like I said, there's been a lot of work on this where L is 2, where we just have only these ReLU units and we don't have these additional linear layers. And in that setting, we could characterize this R2 representation cost, where in particular, we start off with this sort of weight decay expression that we started, and we analyze this optimization problem and show, for instance, that this is equivalent to minimizing over network weights, subject to the constraint that all of the weights feeding into the neural networks have unit norm, and then choosing the overall network that minimizes the L1 norm of this outer layer of weights. So by doing this analysis for 2-layer networks, what we were able to learn is that we really prefer functions that can be expressed via a sparse collection of different ReLU units, where I mean sparsity in the sense of having a small L1 norm. So this is what we end up finding when we train 2-layer networks. So now our goal is to say, can we do something similar when we go from 2-layer networks to 3-layer networks? Can we try to understand, similarly how this representation cost looks under different settings. So as a first step, we're going to use this key fact, which has appeared in many settings, but the earliest one I can find is from Cerebro, Rennie, and Jacola, where they were able to show that if I was to minimize over all matrices W1, W2, whose product is W, the sum of the two matrices Frobenius norms squared, that's equivalent to the nuclear norm. So to the uninitiated, the nuclear norm here is just the sum of all the singular values of the matrix. So we have an immediate connection between the sum of two Frobenius norms squared of two matrices, whose product is W, and the nuclear norm of W. And this can be generalized to bigger products of matrices, say L-1 matrices whose product is W. And if we sum up all of their squared Frobenius norms, what we end up with is a Schatten norm of the matrix, where a Schatten Q norm is basically the LQ norm of the singular values. So we can use this key fact to better understand what's happening when we add linear layers to the neural network. So in particular, we started here by saying that the weight decay representation cost was the sum of these Frobenius norms squared plus the two norms squared of the outer layer weights. And using that key fact from the previous slide, I can rewrite that weight decay cost as being the two norms squared of these outer weights plus the nuclear norm of W. So now if I'm comparing and contrasting the 2-layer and the 3-layer networks, I can say, look, I can write both of them using this same functional form. But when I have a 2-layer network, what I'm regularizing is the 2 norm of A squared plus the Frobenius norm of F squared. Whereas when I add a linear layer, now I'm minimizing the 2 norm of A squared plus the nuclear norm of W squared. So I'm doing a totally different kind of regularization on the weight matrix used to represent the same function. Okay, so maybe going back to this function space perspective, we would say if I have a function f and I want to understand its 3-layer representation cost, then I can compute that by searching over all neural network weights so that I can represent my function using those weights. And among all of those possible weights that fit my function, I'm going to choose the one that minimizes the 2 norm squared of A plus the nuclear norm of W. And I can generalize this to additional linear layers as well. Okay, so what does this mean? How do we interpret this? So here I'm just rewriting this representation cost. And at first pass, we see, oh, well, there's a nuclear norm here. And we generally know that when matrices have lower rank, then they have smaller nuclear norm, loosely speaking. And so initially we might say, well, when we look at this representation cost, it suggests that we prefer functions that can be represented with a lower rank matrix W. So what does that mean? Well, when W is low rank, it means that all of the WKs, all of the weight vectors feeding into each one of the different ReLU units, they all lie within some low dimensional subspace. And the common vernacular in this area is to say that what this means, when we say all these WKs lie in a low dimensional subspace, we say that the ReLU units are aligned. And so we can think of this using a little toy example here, where I'm showing 2 different functions that are defined over a 2-dimensional space. I've got both a top-down view and then sort of a 3D view of the function. And then in addition to showing the function where the color corresponds to amplitude, I'm also showing some contour lines of the function. So on the left, I've got a setting where the ReLU units are not aligned, where the corresponding matrix of weights W might be very high rank or full rank. And so when we look at this function, we see that there's a lot of complexity, and in particular, the contour lines can be quite complex. And in contrast, if we were to have a similar function, but force the ReLU units to be aligned, then all of the weight vectors lie in a low dimensional subspace. And what we see is that the contour lines now are all parallel to one another. Or looking at it from this perspective, what we're seeing is that there are some directions along the contour lines in which the function has very, very small variation, is almost constant, and other directions in which there's a significant degree of variation. So this is the first pass intuition. And here I can even show this maybe from a slightly different perspective. So I'm going to show you what happens when I take a finite set of samples and try to interpolate them. And I'm going to learn an interpolant using a 2-layer network or a 3-layer network or a 4-layer network and show that interpolating function. So when I look at this, and I'm just moving it around so you can see it from different directions, what we see is that in all 3 cases, we learn a function that interpolates the samples. But what we're seeing is that as we add linear layers, we get more and more alignment, in the sense that here, when I've got 2 linear layers, if I were to look at the contour lines of this learned interpolating function, they're much closer to being parallel to one another than the contour lines that I get with, say, a 2-layer network. Okay, so that's a reasonable first pass intuition, that somehow adding linear layers induces some sort of low rankness in our weight matrices, and that manifests itself in functions that have small variation in some direction. But that intuition alone is really insufficient. Really, there's an interplay between the amount of alignment that we see between different ReLU units and some notion of sparsity. And it's only really by understanding this interplay that we really understand these representation costs. So in order to drive this point home, I'm going to show you 2 examples. One is going to be where our intuition is correct, and then I'm going to make a subtle change and the intuition will be wrong. And this will emphasize why just using alignment as a rule of, as a way of understanding this is not really complete. So in this toy problem, I've generated training samples that lie on 2 different rays, and those rays are separated by an angle of 0.55 pi. So on the left here, what I'm showing is the function that I would learn by training a 2-layer ReLU network. So this is an interpolating function that minimizes my 2-layer representation cost. And in contrast, over on the right, what I'm showing is the interpolating function that we learn if we were to train a 3-layer network. So we've got 2 linear layers and 1 ReLU layer. And so we can see that when we train a 3-layer network, we see this alignment. We get perfect fit to our data. We're still interpolating, but we get a very different interpolating function. And in the titles of the plots here, we can actually, I'm going to show you how we actually get numerical values for these quantities, these representation costs that we've been discussing. So for instance, for both of these functions, I can compute the 2-layer representation cost R2. And so we see that the 2-layer representation cost is 1.3 over on the left and 1.8 over on the right. So this tells us explicitly that when we minimize the R2 representation cost, this unaligned network is what we would find, or this is the interpolating function that we would find when using a 2-layer ReLU network. And in contrast, If we look at the 3-layer representation cost, it's smaller over here when we have aligned units, which is exactly what our intuition would tell us. So now what I'm going to do is I'm going to keep this setup almost exactly the same. The only thing I'm going to change is the angle between the two rays. I'm going to change that to 0.52 pi. And so again, on the left, I've got the function, the interpolating function I learned when using a 2-layer network. And on the right, what I'm showing is the best interpolating function that has aligned ReLUs. But perhaps counterintuitively, the 3-layer representation cost with aligned ReLUs is 1.5, whereas if we have unaligned ReLUs, it's even lower. So this is an example that we were able to construct using the theoretical tools we built that shows a case where having linear layers does not force us to have aligned ReLU units. We don't always get alignment, and that's because there is this sort of more complex interaction between alignment and sparsity, as I mentioned before. So the representation cost really has to tell us more than just alignment. Okay, so how are we going to do this? Well, the first thing we need to do is note that there's some notion of scale invariance. So if I've got a weight matrix W and outer layer weights A, I could scale W by some scalar lambda and divide A by lambda and represent exactly the same function. And that's kind of generally true when we have these ReLU networks. So when we analyze representation costs, we really have to account for that scale invariance, right? We don't want to have a misguided understanding of what the representation cost is just because we didn't account for that invariance. And so with that in mind, I'm going to define a new quantity here, phi sub L, which explicitly minimizes the representation cost across all possible rescalings. And we can write our representation cost for a function explicitly in terms of this phi function. So once we do this, for example, if we had a 2-layer network, we can solve this optimization problem and get an explicit form for it that corresponds to the sum over all the hidden nodes of the outer layer weight and the 2 norm of the inner layer weight. And the big question is, well, can we get similarly informative and helpful expressions for deeper networks? So here's a first pass at this. And let's just focus on the case where we've got a single linear layer when L is equal to 3. Then this phi function, this sort of scale invariant cost for a network with parameters W and A, is going to be the infimum over all rescalings lambda of a diagonal matrix with the lambda inverses on the diagonal times a diagonal matrix with those outer layer weights A on the diagonal times W. We take that product and we take its nuclear norm to the 2/3 power. So from looking at this, we're getting sort of also a mathematical understanding of why just thinking about the rank of W is insufficient, right? The rank of W, or the nuclear norm of W, could be quite low, but this product could be still large because we really have to think about not only how big the nuclear norm of W is, but really how those weight vectors are interacting with the outer layer weights in A. So to understand this interaction, let's do a little thought experiment here, where we start with a 2-layer network defined by a W and an A that's been trained to interpolate a finite collection of samples. Now, in general, we would expect the rank of that matrix to be high because we just trained a 2-layer network, so there's no reason to expect there to be any kind of alignment. But then what we could do is we could force ourselves to come up with a network that does have alignment, and we can do it the following way. So we can define a subspace S and here it's spanned by some vector that I'm calling W0, and project all of our features onto that subspace. And then what we can do is learn an interpolating network or interpolating function just on that subspace. So by doing this, we end up with a new network, new W and a new A, that interpolates these projected samples. It's still, the way we've done this, it interpolates our original samples as well. But because we had this projection step inserted, what we're ending up doing is, or what we end up with is a weight matrix that does have low rank. So the projection step forces us to have aligned units. And so from this intuition, we can actually use this basic concept to explore the interaction between alignment and sparsity. So first, I'm showing here what I showed on the previous slide, the best interpolating function that we would train, or we would get if we trained a 2-layer network. No alignment. The contour lines are not parallel. Here's an alternative where we force the ReLU units to be aligned, and in fact, that alignment is somehow perpendicular to that subspace that we've projected all of our samples onto. And we can see that from this top-down view, also in a 3D view. And what I'm showing on the bottom here is all of my training samples along this subspace. And what I'm showing is that through this blue line is that we have actually learned a function that interpolates, that perfectly fits all of our samples. Now, alternatively, I could choose I could repeat exactly this procedure, but with a different subspace. In this case, spanned by this particular W0. And again, by forcing myself to interpolate samples after they've been projected on this subspace, I end up with a network that is going to have highly aligned ReLU units. And I can kind of see that here, right? I can see the contour lines are all parallel, or I can see the alignment of the ReLU units in this 3D view. But this is sort of a bad subspace in that when I look at the interpolating function along that subspace, it's extremely oscillatory. And so what the expressions that we've derived show, and what this kind of toy example highlights, is that when we train a network with linear layers, what we're implicitly doing is we're seeking an interpolating function f and a corresponding low-dimensional subspace S, so that f has got limited variation perpendicular to S and a very smooth representation or low R2 cost on S. And so this middle panel is an example of that. So in this middle panel, if this subspace is spanned by W0, then our learned function has almost no variation perpendicular to that, and also is nice and smooth along the subspace. And so this is what we implicitly seek when we try to train networks with these additional linear layers. Okay, so I want to just give a hint at some of the mathematics that underlie this. I had earlier this expression for this phi function, and we actually developed a number of different upper and lower bounds that are tight for this optimization problem. And that's what allowed us to do the calculations that I'm showing in all of these pictures, to say exactly what the representation cost is for different functions, or upper and lower bounds at least for different functions. So we can verify that indeed our intuition that we need this alignment and we need the smoothness along different subspaces, so that's grounded in a mathematical reality and not just an artifact of how we set up some toy example. So in particular, for instance, we were able to come up with exact expressions for these functions when all of the weights lie on a one-dimensional subspace, which is what I was showing when I made my pictures, or when all of the weights are orthonormal to one another. And so we can get exact expressions for what these representation costs look like. We can also rewrite the representation cost as a slightly different optimization problem over where we maximize over all matrices Q that have operator norm bounded by 1. And this by itself isn't super interpretable, but by using this lemma, we're able to generate lower bounds on the representation cost for various settings by simply choosing different Qs to plug in to this expression here. So this immediately leads to some of the lower bounds that I've been showing in some of my pictures. So I want to conclude with a very quick case study where, again, we've got features on 2 rays. And in this case, the rays are defined by 2 vectors that I'm calling W1 and W2. So when I've got training samples like this, I can actually write down an expression for an interpolating network where for this network, all of the ReLU units have input weight vectors that are either exactly equal to W1 or exactly equal to W2. So all of our ReLU units are going to be aligned with one of these 2 rays that support our samples. One of the reasons that these rays are nice is because it then allows us to immediately write down an alternative interpolating network with aligned ReLUs using a closed form expression. So I'm going to define W0 here to just be the difference between my 2 rays, W1 and W2. And I can write down an expression for an interpolating function where all of the ReLU units are aligned with W0. And so here, I'll just show that again, where you can see that I've constructed 2 functions, one with unaligned ReLU units and one with aligned ReLU units. So in this simple setting, for instance, what we can prove is the following. So in particular, the representation cost with unaligned units for a 2-layer network is always going to be smaller than if I have aligned units. So in other words, if I do not have linear layers, then I always prefer a function that interpolates my data that doesn't have this sort of alignment property. But in contrast, if I have linear layers, so that I'm minimizing, for instance, the R3 representation cost, then sometimes having aligned units, which is what G had, is better. And whether or not it's better depends on the angle between those 2 different rays that support our samples. And this is supported by our empirical experiments. So I showed you this kind of counterintuitive example a few slides ago. And in fact, our theory predicts exactly when we're going to prefer alignment versus not prefer alignment. So my ultimate hope is that by understanding these representation costs, and in particular by taking this notion that what we do when we add linear layers is we try to find subspaces so that there's minimum variation along the subspace and almost no variation perpendicular to the subspace. The hope is that we're going to gain some insight into, say, the robustness of networks to slight perturbations in samples, or to how we respond to spurious correlations. So for instance, where's here, right, we can imagine that if we had a network like this, if I were to make a slight perturbation to a function, I could get a totally different output. Whereas when we learn nice functions with ReLU alignment and smoothness along the learned subspace, then the behavior away from our immediate training samples is much more predictable and smooth. And so the hope is that by studying these representation costs, we're going to gain that additional insight, and it'll help us to design networks that are better at accounting for these things that have been pervasive challenges. A little bit more generally, my hope is that by understanding these representation costs, we're going to have a new suite of tools for assessing generalization, when we're going to have errors, or how much data we need in order to keep error levels controlled. And I think, an important direction of future work is to say, can we take these representation costs and use it to characterize or better characterize the kinds of function spaces associated with multi-layer nonlinear neural networks. And I think there's some really nice connections with ideas such as mixed variation function spaces that have appeared in the literature, and that by pursuing research along this direction, hopefully we'll be able to do things like derive minimax error decay rates and sample complexity bounds. So with that, I just want to leave up here information about where you can find the paper that goes into some of the more mathematical details, and I would be more than happy to answer any questions.
Thank you, Rebecca, for the very exciting talk. Are there any questions?